So, topic for today again is light or electromagnetic waves. Now to actually start into this, we need to give a little bit of a historical perspective as to what were the things that people had been discovering and what were their approaches to how these concepts work. So back in the 1800s, this is when a lot of the material is really being worked on. So chemistry is getting leaps and bounds during the 1800s as the periodic table is filled out more thoroughly, as properties and similarities between elements are being figured out. Physicists are also working out to figure out what's light? How does this work? And there were two groups. There was a group that said light is a wave. Light is a wave. And they had a few pieces of evidence, largely how light interacted or how light traveled. And light exhibited very similar properties to other waves in that it diffracted, so diffraction, reflection, and refraction. All properties of how you can go about changing the direction of a wave, and light also does these. And we'll explain a little bit more about what these are a little bit later. However, the group that believed light is a wave had a bit of an issue, and that was that they did not have a medium for light. What is light's medium? All right. The counter-argument, or the other section, was light as a particle. As a particle. Now, people who believed in light as a particle had some evidence that it should clearly be a particle. The first one was what we know as the photoelectric effect. Photoelectric effect. Where we can take a piece of gold plate, and we can shine some blue light on it. And when we shine blue light, electrons bounce off. And we know that electrons bounce off because if we hook up a voltmeter to this, the leaving electrons cause a potential difference between the two sides of the plate, and that registers as a voltage. Good with that idea? Okay, so because of this, light must have momentum. Light must interact somehow to knock these electrons out. Light must be a particle. To have momentum. People who believed light is a particle also had the advantage of being able to explain how light travels through a vacuum. We could create vacuum tubes in the 1800s, and we were getting the idea that space could be one. So how does light get from the sun to the earth if there's no medium? Well, if light is a particle, that's pretty easy. Light travels through a vacuum. What do they have for issues, though? Light also travels through glass, and glass is a solid. All right, so both had supporting evidence, but both also had some issues with their model. Okay. So what we're going to do now is we're actually going to go back and define diffraction, reflection, and refraction, and look a little bit closer at how the proof of those actually came about. So starting with diffraction. You guys observed diffraction in your simulation last week. The second simulation with the wave pool, you were able to create a section that had a small slit, and you created waves from one location. As those waves reached the slit, they propagated or continued all around that slit. They didn't make a straight line. Yep. So if light was a particle, and light would hit this slit, it would just go straight through and hit the wall at the back. However, light is evidently a wave, because when it reached this gap, it acted just like water does. It curved and made new paths as it traveled beyond the edge. So when a wave passes an edge, the wave bends. So what I have here is just a low wattage red laser. And you can see the dot on the back. Now, if light is a particle, and I try running that through a very, very small slit, so I have a pair of razor blades here that are put up right against each other. If light is a particle, it will go straight through and continue to make a dot. If light is a wave, because there are edges here, the light will bend. What do you see? There's the dot. I'm just trying to get the positioning right. Okay, it looks like it's spread out, right? Where I can hold it steady enough to get it to show its location. Okay. Alright, so you can see that it spreads out, and actually if you're close enough, let's see if I can get it to show right. Wow, I need to get a mount for this of some sort. So those who are really close to the back there, how many locations that are actually really bright are there? What do you mean? So there's the one in the center, right? There's also one to each side if you look closely enough. So to the side, there are a couple of brighter, well, they're dim by comparison, but there are a couple of bright spots. So you should be seeing something that looks like a bright spot, a dark spot, a relatively dim spot, a dark spot, and then one more bright spot on each side. And what that is that's the wave pattern of the wave of light that we're sending down there. So because this is angled, using a little triangular geometry, you'd recognize that this distance is larger than this distance is larger than this distance. Because of that, what part of the wave is hitting the wall at each point is different. The spots where it's brightest are the crests of the waves. Spots where it's darkest are the troughs of the waves. Okay? So we find that we actually have this diffraction, this bending of light as it passes those edges. People good with diffraction? Do we have any questions on it? Leave it up there for a moment? Yeah, I can do that. Okay. Next one on our list. Reflection. Reflection is the changing of direction of a wave because it reached a boundary. The change in direction of a wave as it bounces off a boundary. As it bounces off a boundary. If you need me to explain more about what reflection is, go stare in a mirror until you figure it out. Okay? However, to give a more extreme example than just looking in the mirror, we have what we call complete internal reflection. What this means is that the light ray is going to bounce off an object or off a surface and continue to bounce off that surface unless it gets over what we call the critical angle, meaning an angle where it's just too steep to bounce. Let's turn it back on the laser. This is a fiber optic tube. So people over there should be able to see that it's red here. Okay? And if I turn this on the other side, you should be able to see that it's red. And the other thing you should notice is that there's no laser dot on the back wall. Okay? There's where it should be. No, it's not. Okay? And to prove that this is actually bouncing around inside here, so you can actually see it bouncing off the sides of the fiber optic wall. And as long as I don't get it too steep of an angle, it doesn't exit the fiber optic cable. And I should be approaching the, yep, okay, now I'm too steep of an angle, and I've got a dot appearing on the, or really a line appearing on the back wall. And there. So that angle is right about in here somewhere. And you can see it bouncing off the sides of the fiber optic cable. Okay. When I was taking, I think, my third college physics course, we had a professor who loved to teach for the green laser pointer. So green's pretty high energy, pretty bright, and she'd point at the board and talk, and then still with the laser pointer button depressed, talk, and just kind of flail around at the class. The number of times you'd have green laser blind you was ridiculous. All right, next one on our list is refraction. Refraction is the bending of light because of a change in wave speed. Or sorry, the bending of a wave because of a change in wave speed. The bending of a wave due to a change in wave speed. How do you change a wave's speed? Yep. So really this is due to a change in medium. So as sound goes from air to water, it changes the direction in which it travels. As a rope wave changes from a thin rope to a thick rope, it angles at the transition point. As light goes from air to water, it changes its direction. So if we're standing here on this shore, now we got a fish here. Now we decided we're hungry, so we go and we fashion a spear. Okay? Where do you want to aim to spear the fish? No, it doesn't depend on where the sun is. It's always the same. Below it. You may aim here, but the fish is actually here. Because the light coming from the fish, yep, the light coming from the fish changes medium as it goes from water to air, and therefore it angles. So while it looks like the fish, thank you, is actually here, it's really emitting its light from much lower. Okay? So refraction, change in the path of a wave due to a change in wave speed. All right, questions on any of these three? Refraction, reflection, diffraction. I think diffraction's the coolest because it's not what you'd expect. The other ones, yeah, you see that all the time. Okay. Also, refraction. This is your eyeglasses. This is your contacts. As the light passes through your glasses, it changes wave speed. Therefore, it refracts and bends to adjust to your eyes. This is also why individual glasses prescriptions must be different. because the amount of bending needed, so the amount of time it spends in that different medium and the angle at which it's got to come out at have to be very specific because the refraction coefficients are very, very specific. The speed of light in glass is slower, but it is not slower enough that you would be able to physically notice it. Yeah, he does. He saw it. All right. Last piece for waves, or sorry, for light as a wave, and that is the ether. Now, for those who believe that light was a wave, they needed a medium because every other wave had a medium. So the ether was the medium for light. The medium for light. And ether was simply a substance that permeated all of the universe, or permeated the entire universe. A substance that permeates the entire universe. So we're talking about it's through space, it's through solid objects, it's through air, it's through liquids, it's everywhere. And it's consistent. And it also only interacts with light. Only interacts with light. Okay, so somebody asked me about it earlier because I had questioned about it in other classes. And here's where I get to show truly how geeky I am. Anybody in here play D&D? No? No? Dungeons and Dragons. Bummer. There goes that example. Oh well. Well, trying to give the example of what the ether is. It's like, okay, so whether or not you believe in ghosts, the idea of a ghost, you can pass through them, right? So now take a layer of ghosts and coat the entire universe in a layer of ghosts, right? So in D&D, there's a game concept where ghosts live. And it's basically the idea that, well, a ghost doesn't interact with anything, right? They can be there, but they're not actually there. So if we're explaining what the ether is, it's like a layer of ghosts through which light can interact with things. Does it make sense? Well, trying to explain what the ether is as, oh, it's this stuff that permeates all materials, but it's not a gas. Yeah. There was a test, and the late 1800s, late 1800s, a couple of guys by the name of Michelson and Morley decided to do a test to show its presence. Michelson and Morley. And the way they decided to do this is that because the ether only interacts with light, it should not interact with Earth. Earth must be moving through the ether. So if you were to shine a light in the direction that Earth moves through the ether, it would take a different amount of time for it to travel a certain distance because the distance would be different than it would take for the light if it was moving perpendicularly to how Earth moves through the ether. So what they did was they took a laser and they shined it at a mirror. Now this mirror was unique because it had slits in it. And this mirror allowed part of the light to go through and part of the light to bounce up. And then it hit solid mirrors where the light bounced down, back through the mirror, or bounced back, hit the mirror, and came down, and both of the beams ended at a detector. Okay? Now, because the Earth was moving through the ether, that meant that the first beam of light travels in the same direction as the Earth moves through the ether. Then the light that goes here does the same, travels in the same direction as it moves through the ether. Bounces and travels backwards against how Earth moves through the ether, and then perpendicularly to it, compared to light coming out, bouncing off the mirror, going perpendicular, perpendicular, perpendicular. So because of the fact that one direction was moving the same way Earth moves through the ether, and the other was independent of it, if the Earth moves through the ether, then these distances should be different, and therefore the times that it takes to get from in this path versus this path shouldn't be the same. Well, they did the experiment. They did it multiple times to make sure they were getting the right result. And what they found was that the times were exactly the same every time. So the ether didn't exist. And this is significant because the majority of scientists in the 1800s believed this was a thing. Okay? This almost ghostly layer of substance that permeates the entire universe that light can travel in was common understanding. It was what everybody believed worked. Much in the same manner that currently we believe that space and time warp due to mass. We've got calculations in science to show that it works. So did they. Okay? So the idea that this is the commonly accepted idea and was supported by a lot of very well-known scientists, but it turned out it was wrong, wasn't actually unique, because this is how science occurs over the course of time. Everybody believes something, they've got evidence to back it up, then somebody does a new experiment to show something different, and suddenly it turns out it didn't work. And it doesn't work because what we believed wasn't true. Okay, so given that light no longer had a medium, that gave the guys who were believing that light was a particle a whole lot more weight to their words. However, it still didn't explain refraction, reflection, or diffraction. Now this next part, it just blows my mind that nobody came up with it before this. But the next part required Einstein in order to explain it. So if the ether doesn't exist, but light is a wave, and light shows tendencies to be a particle, what kind of conclusion do you think you might come to?
It's different.
It's different? Okay, what other kind of conclusions?
It's a special wave.
What do you mean?
One of those waves doesn't exist.
It's a wave and a particle. Congratulations, you did the exact same thing that Einstein was required to do. I mean, really, nobody else got that before him? How did that not happen? Light is both a wave and a particle. So Einstein brought about the understanding of the dual nature of light. I mean, really, we've been talking about it for less than half an hour, and we were able to come up with that. How did nobody else do this? Dual nature of light. Light is both a wave and a particle. It is both a wave and a particle. Okay? Well, that explains how it gets through space and gets through a vacuum. It's a particle. It doesn't need a medium. Okay? But that doesn't explain why it can pass through things like glass if it's a particle. Well, it's a very unique particle, and the particle its name is a photon. Right? And a photon is a bundle of energy that travels as a wave. A bundle of energy that travels as a wave. Meaning that if I were to draw a photon, it'd look like a whole bunch of little energy vectors twisting up on each other and going in whichever direction, bound to each other somehow, and then it would go through space like this. Okay? So it's got a whole bunch of little energy bundled up together and it goes through space. Now, I will tell you right now, there is going to be a quiz or test question that is going to ask, what is the particle of light called? And the options are going to be a photon, a proton, and an electron. And someone invariably will tell me that light is a proton. No, there is no R in this word. Photons, bundle of energy. Protons are what we talk about in chemistry, and they have charge. Yeah. Yeah, go ahead. Okay, so now no one was going to miss this question on what is the bundle of energy that light is called. It is a photon with an H. Okay? Okay, so to build on this idea of the photon just a little bit more, we need to take a look at what we already understand about how we've been taught science so far. So when we were talking in November, we told you guys conservation of energy, right? What's conservation of energy?
Can't be created or destroyed.
What can it do?
Transmute.
Change forms, right? Okay. What was or at what age, what class, what grade was the first time you heard about conservation of mass? Conservation of mass. When was the first time you heard about it? 6th grade? Okay. So some people, maybe 7th grade, some people probably weren't paying attention until 9th. But probably somewhere in your middle school career, you heard about conservation of mass. Mass can't be created or destroyed, it can just change forms. I mean, at the very least, you heard it over here in chemistry when you took that, if you took that. Okay? So, really, those are not entirely true statements. Because the law of conservation of mass and the law of conservation of energy are really the same law. Because mass and energy have a much tighter relationship than we've really talked about so far. So the law is really conservation of mass and energy. Oh look, that was a difficult name. And instead of being mass cannot be created or destroyed, it can just change forms. And instead of being energy cannot be created or destroyed, it can just change forms. It's mass and energy cannot be created or destroyed, they can just change forms. Now, the interesting aspect to that is that mass and energy can change forms and they're encompassed under the same law. And it's not two individual laws. That means that mass and energy can change back and forth between each other. Mass and energy can change between each other. Okay? And this is a concept that Einstein brings around in his publication, Special Relativity. And it's the easily most famous equation in all of science. Now, 99.9% of Americans will probably be able to tell you E equals mc squared. Einstein, science, yay. However, they probably also have absolutely no understanding as to what it means. Okay? E, of course, being energy, m being mass, and c being the speed of light. This is the amount of energy produced when mass changes into energy. This is an equation used for situations like fission, nuclear bombs, radioactive decay, nuclear power plants, and fusion, the sun. All right? So fission and fusion operate under this equation, this relationship, that shows how energy transfers to mass, how mass changes into energy. Okay? So really they're the same concept and part of what defines a photon and why a photon can actually pass through certain materials, such as glass. Because it isn't mass, well, it's a bundle of energy, not a bundle of mass. Why does it interact with some things and act as though it has mass? Well, because in certain situations, mass and energy convert between each other. And when we're talking about this photoelectric effect that we mentioned earlier, that on this page, it's the light effectively has mass because it has energy. So when it strikes an electron, that electron gains that much energy as the light loses it, and the electron bounces off. All right. Questions on this stuff? Yeah. No.
How can, you can measure the weight of light with a scale.
Wrong. You can measure the effective weight of it with a scale. You cannot measure light with a scale. If I have a bundle of photons, a bundle of pieces of light, it has no mass. If I use that as like momentum and I shine it on something, the energy that it's using can act as though it has a momentum as it bumps into things and gives them that energy. So while it has no mass, meaning that it doesn't have gravity, It does not warp space and time. You cannot measure it on a scale. It does have an effective mass, meaning it acts as though it had this much in collisions and if you're trying to produce energy or mass from it.
But how can it collide if it doesn't exist?
It does exist, it's energy. And it can interact as though it had mass in certain situations. Let's see here. For that, probably like 2 or 3 people in here who have read anything about quantum mechanics versus relativity, it kind of has the same nature in that you can either pick whether quantum mechanics or relativity applies to a situation, but we can't rectify the two. Photons do the same. You can pick whether it acts as as a wave or as a particle, but we really have no justification for rectifying the two. You can just pick which one it works as. Yeah, whichever one's more applicable to the situation. All right, so we've got what is light. We've got how does light interact with things. What we don't have is the different categories of light. And this is the electromagnetic spectrum. Okay. Electromagnetic spectrum, we're going to start with radio. We're going to go to microwave, down to infrared, visible, ultraviolet, following ultraviolet, we've got X-ray, and finally gamma ray. Yep. Okay. So, as we move down this list, we are finding waves that have higher frequency. Higher frequency. Now, because these are all light, they all move at the exact same speed. They all move at the speed of light. Well, if the frequency on a wave changes while the speed stays the same, what other property must also change? Wavelength. So in this direction, these have longer wavelength. In a mechanical wave, what property of a mechanical wave tells us how much energy a wave has? Amplitude. Good. In an electromagnetic wave, it's related to the frequency. Higher energy. Okay? Let's see. Am I completely out of paper? Nope. Okay. All right. So, we'll start at the bottom here with gamma rays and we'll move up. Nope. Gamma rays. Where have you heard of gamma rays? I heard the sun. What comic books? No. No. All right. Somebody who reads comic books or at least saw the movies. How does Bruce Banner change into the Hulk other than he just gets mad? His research in the comics was that he worked a lot with gamma radiation. And gamma radiation caused his cells to mutate. Gamma radiation actually does cause cells to mutate. Causes cells to mutate. What do we, in reality, call it when cells mutate? Cancer. Okay? So, while in the comic book world, Stan Lee decided that the mutation was going to be uniform and cause him to Hulk out, in reality, mutation of cells is cancer. Okay? So this was a large thing that was caused by the drop of Fat Man and Little Boy, the bombs that were dropped on Hiroshima and Nagasaki. Because if you were not initially killed by the explosion, then the radiation sickness, the gamma rays that you were affected by, caused cells to mutate. They caused sickness because your cells were now trying to do things they were not supposed to. The energy from these gamma rays basically have slowly killed way more people than I believe the initial bombs did. Okay? So, gamma rays, we see these in nuclear explosions. We also see them being created by the sun. Radioactive materials give them off. And we can use them for radiation therapy. While some gamma radiation will cause your cells to mutate, concentrated gamma radiation kills them. So when people go in for radiation therapy for cancer treatment, what is done is they take a very focused band of radiation, of gamma radiation, and they focus it in on the cancerous cells. And then they basically just blast these cancerous cells with gamma radiation until the cells die, so they're no longer able to replicate their mutated versions. Really, this is about as close to it comes as saying you're fighting fire with fire, other than actually fighting fire with fire. Simply because this is using something that can cause cancer to try to cure it, or try to kill it. Okay, a couple other things here. It's blocked by lead. Or our atmosphere. Okay, next one down the list, X-rays. X-rays are used for X-rays. All right. They're able to be used for X-ray machines because, like gamma rays, they're only blocked by lead. Blocked by lead or the atmosphere. If you have enough of other materials, or you have thick enough materials, yeah, it can be blocked by it. Lead is a good example of why what blocks these, because lead is very dense and doesn't allow the radiation to pass through it. Less dense materials are able to be passed through very easily, which is why they work very well for X-ray machines. The radiation passes through your skin very easily, but not through the bones as well. So it gets partially blocked by the bones and mostly goes through your skin, so you're able to make a picture of it on the back as the X-rays basically pick up what radiation made it through your arm, or through your jaw, or through, you know, whatever you may be getting X-rayed.
So, like, when they put, like, if you have, like, when you get an X-ray and they put
That lead vest on you? Yeah, it is totally a lead vest. Also to note, where does the X-ray technician stand when they take you the X-ray of your teeth at the dentist? Outside of the room, behind some kind of wall. What they're doing is they're reducing the amount of X-ray radiation they pick up. Now, you and I probably only get X-ray radiation 2-3 times a year. An X-ray technician would get it 2-3 times an hour. All right? So they would be at high risk for cancer if they were to stay in that room all the time. However, by leaving the room and not being where the X-rays are constantly being emitted, they reduce their chances of it significantly. So blocked by lead of the atmosphere, used in dentistry. If you were to decide to be an astronaut, X-ray and gamma radiation would be one of your concerns because you'd be outside the atmosphere. And actually, one of the things they have to monitor with astronauts when they do spacewalks is how long they're out in space, simply because they get an extra amount of gamma and X-ray radiation that can be cancerous. So that's a concern for astronauts when they return, is to be monitoring how is their life proceeding, because you want to make sure they're not developing cancer, and they're at special risk for it because they have been subjected to more gamma radiation in higher intensity and more X-ray radiation in higher intensity than is normal for most people. Okay, so also causes cancer. Next one on our list, ultraviolet. What kind? Causes skin cancer. I was being less specific. Okay? Causes skin cancer. Where does it come from? Sun. Emitted by the sun. Unfortunately, our atmosphere does not protect us largely from ultraviolet radiation. Especially if you're at higher elevations, then there's even less atmosphere to protect you from the ultraviolet that we do get. So this is something that we actually have to be concerned about. And as a redhead, I truly do not understand tanning. Like, I don't get why people do that, because, first of all, I just burn. But second, it causes skin cancer. And even if you don't necessarily burn every time, your chances of looking like a raisin by the time you're 30 go up astronomically. So I just do not understand it. Okay? Ultraviolet radiation causes skin cancer. What do you use to protect yourself from ultraviolet radiation? Sunscreen and clothing's a good option. I also heard sunglasses out there. Alright, sunscreen. First of all, how many people have heard the myth that after SPF 30 they're all the same? Okay, myth. However, for certain individuals, it may not matter, because you may not be susceptible to skin cancer as much. Johnny, I'm guessing you don't get sunburned very often. Ramada, I'm guessing you never get sunburned. Okay, so yeah, it is. You guys probably don't need sunscreen nearly in the capacity that, say, Paige or I would. Okay, so SPF say 55. I've burned through that before. Whereas 55 is probably more than good enough for most of you. There is a difference, but only certain skin types are actually going to care. Yeah, no, I'm pretty sure that if it weren't for Vlad the Impaler, vampires would be based off redheads. And the whole burning up in the outside, yeah, no, I think it's a thing. No, but I do know a redhead who does. Alright, so, ultraviolet radiation. Sunscreen, talk about it. Next one. Sunglasses. Right? So I thought about mounting a pair of ear sights to these, but it became impractical. What properties of sunglasses make them better than others? What properties of sunglasses make them better? Polarized. That's what I'm looking for. So polarized lenses block more light than non-polarized lenses because light is polarized. Well, what do I mean by light is polarized? Alright, by polarization, what I mean is that light travels in a specific direction. Light travels in a specific direction. So I could have one light wave that goes like this, and another light wave that goes like this. Okay? So on a polarized lens, if I've got my light ray going up here, and I've got my polarization here, if it's wavering perpendicularly to the polarization, it hits one of the lines and it stops. However, if it's waving parallel to it, so in and out of the page, passes straight through them. Okay? Now what that means is that by taking a polarized lens, I block out half the light that I'm looking at you guys with. Okay? By taking two lenses that are polarized in the same manner, I might block out just a little bit more, but not a whole lot. You can tell that there's not much difference between the sides or the overlapping part, right? But if I turn one 90 degrees, I've now adjusted so that the polarizations are perpendicular to each other. And I can block out individuals that I don't want to see anything more of. Okay, so if you didn't see, polarized in the same direction, polarized perpendicularly. Also, kind of cool effect, it becomes a mirror. So when these are polarized perfectly together, it reflects all the light rather than just blocking it. Okay?
Why do people wear
Sunglasses? I have no idea.
Alright. If you do this with sunglasses, yes, you can pop, like, polarized sunglasses, you can pop the lenses out of them and do the same thing with. Also, certain cell phones, the light coming from them is polarized. And if you turn your cell phone just right while wearing polarized sunglasses, you can't see your screen anymore. I know it works on mine. I'm not sure if it works on the current iPhone generation. But it's worth noting that some phones are polarized, so if you turn them, yeah, you will stop being able to see your screen. Yeah, some windshields are definitely polarized, and especially near the top and the bottom. There can definitely be an issue. All right, we'll see you tomorrow.